Hope everyone's doing well. Good morning. Set up. Cool. Okay. Morning. Okay. I think we're ready to go. All right, so just continue on to our next two here. All right, these FRQ practices or practice problems. So number 3, from our third packet, grass clippings are placed in a bin where they decompose. For 0 to 30. Nope, that's not writing. There we go. So the amount remaining is given to me by this function a of t. A of t measured in pounds, t is measured in days. Part A, find the average rate of change over the interval 0 to 30, indicate units of measure. Good morning, Hayden. Another crushing victory over RJ. Knew it. He never stood a chance. He'll come in here in a minute and claim that he was, on his phone, so he couldn't comment. But, all right, RJ. Okay. So average rate of change. So this, pretty much directly indicates to me we're just using the average rate of change formula. I'm not even really doing any calculus particularly. So I have the interval that I want to do the average rate of change on. So let's just do average rate of change. So of a of t, so a of 30 minus a of 0 divided by 30 minus 0. I'm on my phone. Chatty. Yeah, same. I'm also on my phone. Good thing I downloaded Smart Notebook on my phone, and then I can just write on it here. Okay. All right, so a of 30 minus a of 0. We have our function a defined up here. I'm actually going to pull up my calculator. So again, I'll go ahead and enter this function in here just in case I need to use it multiple times, so I don't have to type it in a bunch. I can just type it in once here. Okay, so there's that function. Pull it up here. Okay, so I just typed in a of t into my y1. I think it'll be helpful to have it there. Okay, so now I can call that function as I need. So I'm just going to do the whole average rate of change formula here. So a of 30, so alpha trace y1 of 30 minus alpha trace y1 of 0 divided by 30 minus 0. All right, like I've always recommended, the less times that you have to hit enter on your calculator, the better off you're going to be. Negative 0.196. Oh, 197. Sorry. Oh, erase. Okay. And then indicate units of measure. So what the heck is this we're talking about? Well, as it tells me, A of t is measured in pounds, right? Pounds of grass clippings. And t is measured in days. So an average rate of change is negative 0.197 pounds per day. Voila. Right. Part B, find the value of a prime of 15. Using correct units, interpret the meaning of the value in the context of the problem. So this is one of those things where we have to say, not only just calculate the number, but say, and then not only just say units, but like, what does this actually mean? Okay, what is this telling us? So a prime of 15, I can use my calculator again on that because I already have a stored in there. So I'm going to go math 8 for derivative. The derivative of that function that I just had, so y1. And then I want to evaluate it at 15. Should be. Whoa. There we go. So a prime of 15 equals negative 0.164. All right, great. Now, again, what does that actually mean in the context of the problem? Well, let's look back at A. All right, A represents the amount of grass clippings remaining. So if I take the derivative of that, okay, then that's telling me how much the amount of grass clipping remaining is changing. Right? So since my derivative is negative, then it tells me that that rate is, or that amount is decreasing. So the amount of grass clippings in the, what was it, in the bin, it's decreasing because I see that my derivative is negative. At a rate of 0.164 pounds per day at t equals 15 days. Right? We evaluated the derivative specifically at 15. So we have to keep an account. That's plays a very important part in our answer. A just represents the amount, so A prime means, the rate. Part C, find the time t for which the amount of grass clippings in the bin is equal to the average amount of grass clippings in the bin over the interval 0 to 30. Okay. All right. So the biggest, or not the biggest, but the thing that jumps out at me the most here is that this says average amount. Okay, now what is the average amount? You might be tricked into thinking that, oh, that's what we did for part A, right? This is negative 0.197, right? Because find. But part A was find the average rate of change. We are now looking for the average amount. Okay, so the question then becomes, how do we find the average amount? So we're trying to find for part C, for what t is the amount equal to the average amount. So what's an expression I can use to represent the average amount over a certain interval? Well, as I'm sure we all perfectly remember, average value, if we have a function of an amount, then we can determine the average value of that amount by doing the integral over the interval, but in front we have that 1 over b minus a. Okay, so right, oops, a, b. All right, the average value. So most commonly missed thing is forgetting the 1 over b minus a in the front. Okay, some of you guys are very familiar with that. You've done it multiple times. All right. So we want to know where is it that these could possibly be the same. All right, well, let's first figure out this right side. We can calculate this, right? We can do this from 0 to 30 and 1 over 30. So actually, let's bust out the old calculator and do it. Let's clear this. So (1 over 30) integral, so math 9, from 0 to 30, alpha trace y1, because that's where we stored our function, a of t, and dx. Okay, so that should just calculate it for us. Great. All right, now I'm going to need to use this value because I want to know when is my function equal to that value, that 2.753. Okay, but I don't want to round this. This is actually a pretty long decimal here, 2.75263510.8. I'm worried that if I round this to like 2.753, that it's going to screw up my answer, right? Because we try to not round until a final step if we can. All right, so I'm going to do something here. I don't think we've talked about this yet. Is we can store this whole number somewhere. So if you look down here at this STO, right above the on button, it should say STO. All right, so that stands for store. So this tells me we can store our answer, and where do we want to store it? Well, it doesn't matter. So this is where we can actually use those letters. So you guys thought that those green letters were just for spelling things out on your calculators and messages to your friend. But we can actually store numbers in there. So let's just store this 2.752635.108 into A. So I'll click alpha and then math so that it gives me the A. So what I've told the calculator to do is, hey, take that number, just put the whole thing in A. That way I don't have to worry about rounding. Okay, so if I clicked A right now and hit enter, oh, yeah, okay. So A represents this whole decimal. Great. Okay, so let me move this for a second. Possibilities. So basically, again, we stored this as A. But you could store it in any letter, B, C, D, whatever, you get it. So now I want to know, when is my function going to be equal to that value? All right, well, we've talked about this a few times now. We cannot ask our calculator to, hey, take this function, when is it going to equal this number? But what our calculator can do, or what we can tell our calculator to do, is say, hey, take this function, when is it going to equal 0? Right? When is it going to be an x-intercept? But we just have to rearrange then. So I'm going to bring that A over to the left side. So now my problem becomes figure out when this thing equals 0. All right, and our calculators can do that. We can bully our calculators into doing that for us. Manipulate the calculator, right? You guys are good at being manipulative, so just now do it with your calculators. Okay, so I'm going to go to my y equals, and I'm going to go to my original function here, but now I'm going to minus that number that I stored, A, so alpha A. How did I change this setting? Go back. Just graph like a line. Okay. Also, good morning. Welcome, RJ. Don't you manipulate numbers with the calculator? It's just a chain of manipulation. The calculator manipulates the numbers. You manipulate the calculator. You manipulate the numbers before you put them into the calculator for the calculator to manipulate them. It's just like a cycle of manipulation. You thought the water cycle was important? Wrong. The cycle of manipulation is important. Let's graph this. College Board manipulates me. All right, so as I'm looking at this graph, I'm trying to figure out, remember, we want to know when it's going to equal 0. We want to find an x-intercept. Looks like it's happening off the screen here, so I'm going to shift my window over so that I can see this a little better. So let's go from, I don't know, let's say like 8 to 15. Because again, you might not pick great windows. You might have to just try, oh, okay, actually this window wasn't so great. Let me try a better one. And then let's just try that. Let's see if we can get away with doing that. Ah, okay. It's kind of really flat. Let me try to fix my y's as well. Let's kind of zoom in on the y-axis. So let's, instead of going -10 to 10, let's go like -2 to +2. Okay, that looks a lot better. I can better see what's happening. So mess with the windows. Okay, manipulate the windows until it's a good view for you. And now we're going to do second trace. So calculate. We want to calculate a 0. left bound, right bound. So just pick something on the left side, and then we'll go to the right side. Doesn't matter where, it just has to be on the right side of the x-intercept. Guess? Sure. Thanks for guessing. I appreciate it. I'm trying to take my AP test, and the calculator's over here guessing answers. So I would get t equals 12.415. Click, 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 click. The old clickaroony is what I call it. Why does it say guess? I don't know, man. You can thank John C. Texas, the inventor of Texas Instruments. Not the inventor of Texas, just the inventor of Texas Instruments. It's unclear which came first, the state or him. It's just as we already tried. I do appreciate that. Okay, so do we have to do anything with t? Let me go back. C, find the time t for which the amount of grass clippings in the bin is equal. Nope, okay. So 12.415, I'll go ahead and put units on it. It doesn't tell me explicitly, but why not? Days. So this problem, not so bad. Just have to remember the average value formula. And then if we have an equation that we want to solve, but it's some crazy equation that we don't like solving by hand, well, just remember shift. You can solve equations on your calculator. You just have to manipulate it so that it's equals 0, and then just find the x-intercept. Okay, part D. For t greater than 30, L of t, the linear approximation, ooh, okay, we're doing linear approximations, is a better model for the amount of grass clippings remaining in the bin. Okay. Use L of t to predict the time at which there will be a ½ pound of grass clippings remaining in the bin. Show the work that leads to your answer. All right. So the first thing I need to do is create a linear approximation. All right, so L of t equals, so it says for the linear approximation at t equals 30. So a of 30 plus a prime of 30 times t minus 30. That's our linear approximation formula. Now you might remember this comes from just the slope of the tangent line formula. Except if you take this minus y1 and shift it over, so y1 plus m times x minus x1. Right, this is pretty much exactly what's happening. Right, m is the slope at 30. y1, right, so here's the y value. How do we get the y value? Well, it comes from if we plug in this x value. So if we plug in 30 to a, that would give us that y value. Right, that's all linear approximation is. It's just the point slope form. Okay, you just got to rearrange it. Manipulate it. Okay. So I do need to figure out a prime of 30 and a of 30. So that's right. Let's go to the calculator. Okay, turn it on. All right, let me quit out of that. So I want to just use my original function a. So actually, remember, we changed this y1 because we subtracted that stored value, but we don't need that anymore. So I'm going to delete that. Make sure you do that, otherwise it'll throw you off. Okay, so I'm going to quit out of that. Okay, so what is a of 30? Let's see, so alpha trace y1 of 30. Okay, it's here. Let's go ahead. I don't know. Here we can write that out. We can store it. You know, either way, let's go ahead. Let's just practice since we're doing it today. Let's store this as b. And make a little note to yourself somewhere. So a of 30. Stored as b. Now let's do a prime of 30. So math 8 x, oops, alpha trace y1, so the derivative of y1 at 30. All right, we got this stuff. Let's go ahead and store that as c. Let's just make our way down the line. All right. Now, going back to our original problem, okay, so we have all of our values here. We know what a of 30 is. We know what a prime of 30 is. The question that we're trying to figure out is at what time, so predict the time, so we're trying to solve for t, that there's 0.5 pounds of grass clippings. Okay, so I'm not plugging in 0.5. I want to know when is this equation going to be equal to 0.5. So that's why I'm setting it equal to 0.5. I want to know what is the time. Solving for time. Let's just solve for t, but with these variables. So first I would subtract b from both sides. Next, divide both sides by c. Oh my gosh. Okay. Hold on. Be right back. RJ, take over. I bet you don't know the last step, RJ. What do I do? Wow. Piece of time. Okay. This is an expression that we can just enter into our calculators. All right, since we have all those values stored, so alpha y equals, make a fraction, 0.5 minus b divided by c plus 35, maybe not. How about 35.054? Not day, yeah, days, sorry. Okay, so if you're worried about numbers being rounded, that that B and the C, since we have to use those in calculations later on, then it kind of concerns me about, is my rounding screwing up my final answer? So you can store those as variables or letters in your calculator and then use them as you need. So that could help. Okay. Sweet. Let's go on to number 4. All right. The rate at which rainwater flows into a drain pipe is modeled by the function R. Okay, so it's important that I know that R is what's flowing into the drain pipe. So that's this crazy function here. Cubic feet per hour, T measured in hours, between 0 to 8. The pipe is partially blocked. Great. It's going to cost a fortune to clear out. Allowing water to drain out, modeled by D of T. And there are 30 cubic feet of water at time T equals 0. So remember, T equals 0, pretty much always we can guarantee represents just like the beginning, what was happening at the start. So at the start, there was already 30 cubic feet of water in the pipe. So part A. How many cubic feet of rainwater flow into the pipe during the 8-hour time interval? So think of what we know. We know a function R that is the rate that water is flowing in. So if I have a function that if I have a function that tells me the rate of water going in, if I actually want to know the accumulation of how much actual water is flowing in, not just the rate of it, then what do we do? What do we do with our function? That's not what I meant. I meant rainwater. Come on, help me out. What do I do? function that tells me the rate of the rainwater going in. Now I just want to know how much rainwater actually went in. Right, so the accumulation of that rate. I'm just going to take the integral. So let me pull up my calculator. So my function 20 sine squared over 35. I don't need to graph it. We'll do math 9 to integrate 0 to 8. y1 dx. So put that over here. 76.570 cubic feet of rainwater. Okay, it doesn't tell us specifically to specify units, but it can't hurt. So there we go. Part B, is the amount of water in the pipe increasing or decreasing at time t equals 3? Well, how do we determine if something is increasing or decreasing? Then we look at the rate. Is its rate positive or is its rate negative? So that's another way of saying, is the rate positive or negative? But well, I guess the rate, the overall total rate, right? So this is talking about the amount of water in the pipe, just in general. Right, so we had a problem like this, I think yesterday, similar, where I know a function, I know R represents the amount of water that's flowing in. I know D of T is the amount of water, the rate of the water that's flowing out. So I just need to compare which one of those is more, which one is greater. Right? Because if the water is leaving faster than the water is coming in, then I know that amount of water in the pipe is decreasing. But if the water is leaving slower than the amount of water that's coming in, then that water in the pipe must be increasing. Okay, so we just need to compare R of 3 compared to D of 3. Okay, so I'm going to go to my calculator and use my function. Oops. So R of 3, so alpha trace y of 3. Okay, so R of 3 is 5.086. I don't care about storing the specific value because I'm just comparing which of these values is bigger. And then D of 3, so I'll go ahead and enter in for Y2 here. I don't know if I need to, but I might. Negative 0.04. x cubed plus 0.4 x squared plus 0.96 x and then I'll go back through and just plug in 3. So except I'll go down to y2 this time. And plug in 3. And we get exactly 5.4. Right, so that tells me that R of 3 is less than D of 3. So the rate going in is less than the rate that's going out. Okay. So since R of 3 is less than D of 3, then the amount of water in the pipe is decreasing. Right? The water's leaving faster than the water that is coming in. Again, we had a very similar problem yesterday when we were talking about, which one was it? Yeah, part C here for number 2 is the amount of unprocessed gravel increasing or decreasing. So we just compared this rate, the rate in compared to the rate out. So same thing happened here. The rate in was lower, so that means the amount is decreasing. It's the same answer that we get here. Okay, let's go to part C. At what time t, 0 to 8, is the amount of water in the pipe at a minimum? Justify your answer. Okay, so minimum, if I'm trying to find a minimum, and specifically a minimum that's on a specific interval, then I'm thinking about using extreme value theorem. So extreme value theorem tells me I find critical points and I test the boundaries, right? So I'll test 0, I'll test 8, I'll test any of the critical point values, and the minimum has to be on one of those, right? So let's do it. So first, for part C, okay, first I just need to create a formula that represents the total amount of water. Okay, so again, very similar to what we did, something we did yesterday. So at any given time, the total amount of water in the pipe is however much we started with. Actually, no, let me write out fully in words first. Okay, starting amounts plus the amount in minus the amount out. All right, that should make intuitive sense to us. Right, total amount of water in the pipe is the starting amount plus however much is going in, subtract away however much is going out, at least up to a certain point. Okay, so now let's actually create a function that fully represents this. So we can call this, we don't want to call it A of t. Oh yeah, we could. Okay, sorry. Our last problem had an A of t. So let's call this total amount of water just A. It's very creative. All right, so starting amount is 30. Okay, plus the amount in and the amount out. So that's not just R and D, right? R represents the rate in, D represents the rate out. Okay, so to actually find the amount, the accumulation, it's like what we did on part A, right? We take an integral. I didn't realize this was an easy plus minus equation. It's a little more complicated once we get to it, but at its heart, yeah, that's the setup. Okay, it gets a little more complicated because we have to take an integral. Since we only know the rates, we don't know the equations for the actual amounts. Okay, but accumulate the amounts, so take an integral, so 0 to t. Okay, so we would want to find any critical points. So A prime, derivative of 30 is 0. The derivative of an integral, all right, whenever we see derivative of an integral, we should note that that's the second fundamental theorem of calculus. So that means we plug in the upper bounds, and that's all times the derivative of the upper bound. So this would all just be times 1 minus, plug in the lower bound, so r of 0 minus d of 0, but times the derivative of the lower bound. So derivative of 0 is 0, so that's times 0. Okay, so actually this part isn't important at all. All right, this is my derivative. Right, which makes sense, right? The A prime means what is the rate, the total change, the total rate of change of the amount of water. Well, if R is the rate in and D is the rate out, then yeah, the overall rate would just be R minus D. Okay, that makes sense. But we do need this A of t for later, so we still do need to write this formula to get to here. Okay, so like always, to find a critical point, so after we take the derivative, what are we going to do with it? We're going to set it equal to 0. Okay. This is great. This is something I can solve using my calculator, right? I can figure out when some expression or some equation equals 0. So let's pull that up. I already have R and D in there as y1 and y2. Right? My y1 is R of t, my y2 is D of t. So I'll make a new function then. So my y3 is y1 minus y2. Y1 minus R2, so that just means R minus D. Since that's what I want to figure out, when is that 0? I don't want it to graph all three of these though. I just want to find the x-intercept of y3. So we can tell it to only graph y3 by, if you scroll over until you're on top of the equal sign. Okay, go to y2 and hit enter on the equal sign, and go to y1 and hit enter on the equal sign. So we can see only the equal sign for y3 is highlighted. All that means is it will only graph y3. So we can tell it specifically which ones to graph. All right, it's kind of like on Desmos whenever you click the little circle to the left of the equation and it will graph it or not graph it or not graph it. Same thing here. So you just either highlight or unhighlight the equals sign. Okay, but we graph. Oh yeah, my window's all weird from last time, huh? Let me change this. So our window, let's see. So remember this whole interval is dealing with 0 to 8. So let's just make our window like 0 to 8 or 0 to 10. The y, I don't know. We'll just I'll put it back to normal, negative 10 to 10 for the y's. Let's see how this works out. Okay. So we're trying to figure out when is this function equaling 0. So I can see 2 points right now where it equals 0, but this one is outside of the boundary, right? 3, 4, 5, 6, 7, 8. 8 is right here. So I only want to find an x-intercept or something that's equal to 0 in between 0 and 8. So I want this. So second trace 0. My left bound, so like I did before, you can click a ton or you could enter in a number. So like -2, or sorry, not -2, +2. So 2, right, this point would be on the left side. So I can say 2. That puts it right there. Now a right bound, so let's just count, let's say 5. So there's my right bound. Guess, sure, guess away. T equals 3.272. So all that this is, though, is a possibility of where could the critical point be happening, right? Or where could the minimum be happening specifically? So now we have our critical point. That's where the derivative equals 0. Now let's actually create a little table here. So t versus a of t. So we have to test the boundaries. So I have to start with 0. And then I want to test my point that I found, 3.272. And then the other boundary, which is 8. So I just need to get these plugged into my calculator. Well, 0, if we plug in, we already know that there was 30 at the start. All right, so that's no big deal. Okay, so remember for a of t, that's this function up here. Okay, so if we type into our calculators, we'd have to use that 30 plus the integral from 0 to 3.272 r of x minus d of x dx. I guess I'll go ahead and do that, or I'll show you. Okay, so 30 plus math 9 0 to t, but t in this case we want 3.272 r of x minus d of x, so that's y1 minus y2 dx. $27.965. Okay. And now I just need to do the same thing, but for 8. Another calculator thing that I can't remember who I was having this conversation with, but if I wanted to type in, I need to type in this same equation again up here, but instead of 3.272, I just need to plug in 8. So I don't know if you know that you can just scroll up to this thing and hit enter, and it'll put that whole thing there again, except now you can change it. So now instead of 3.272, I could just change that to 8 instead of having to type everything out again. So we would get 48.544. Again, we're looking for the minimum, so we're just looking for the smallest value. Right? I don't think the question asks when does the minimum happen. I think it just asks what the minimum is. Nope, that's the grass clippings problem. Sorry. Oh, no. So part C asks specifically at what time is the amount of water at a minimum. So it's not asking what is the minimum. It's just asking at what time. So I really care about, for my answer for part C, 3.272. So as I write my answer, the amount of water in the pipe is at a minimum at t equals 3.272. What is that? Hours? Right. We know that's the minimum because this A of t is the smallest one out of these 3, so the minimum happens here. This value is the actual minimum, but this value is when the minimum happens. And our question asked, when does the minimum happen? So we just have to pay attention to what it's specifically asking. And part D. The pipe can hold 50 cubic feet of water before overflowing. For t larger than 8, water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. Write, but do not solve, an equation involving one or more integrals that gives the time w when the pipe will begin to overflow. All right, great. So basically we want to know when is the pipe going to overflow? Well, we know the pipe overflows if there's more than 50 cubic feet of water. So if we have an equation for how much water is in the pipe, let's just set it equal to 50. Well, guess what? We already have an equation for the total water in the pipe, and that's this thing. Right, so we just want to know when is this equation, this whole A of t, when is that going to equal 50? Right. Now this specifically asks for time w, so we'll use w, but so set it equal to 50, 30 plus the integral of 0 to, I'm not going to put t because again I want to know what is the w that it'll hit 50. So there we go. Done. Don't even have to solve it. We could solve it. Well, maybe. And that's it. So keeping, I don't know if I actually mentioned or not. I mean, you can see because you have the things I sent to you. But for example, on like the PDF. Okay, so this is the PDF of what I sent you. Right, it has those. These are the for this packet. But here's this equation. That's question 1, 2, 3, 4. These are all these are all calculator-based FRQs. However, if you continue scrolling, you get 4 more questions that are also not calculator-based. Okay, so but have similar style of questions. Okay, so for example, like average value or things like that. So this is additional practice. Every packet that I've sent you so far, so we're on the 3rd one right now, but the 1st packet, the 2nd packet, and this 3rd packet, they all have 4 no calculator problems at the bottom. We've been doing the 4 calculator ones, but there's also 4 non-calculator ones, so also super useful to practice. Okay, you guys have to be able to do FRQs where you just look at a problem and you have to dissect information and determine what you need to do and what you need to find. And also for each packet that I've sent out in each answer key, so this goes through 4. This has the points and answers for all of what we just did, 1, 2, 3, and 4. But then if you scroll down, there's also the no calculator section here. Okay, that has the answers as well. And this, again, this is true for every packet I've sent you. Okay, so far you have 24, just from these packets, you have 24 FRQs, calculator and no calculator, that you can practice. On the AP AFA, there's, I think, 3 sets of FRQs for AB, 3 sets of FRQs for BC. All right, so that's 24 more FRQs. Okay, so you have a ton of FRQs to practice on. A ton. Plus, we're still going to do 2 more packets of these in class. So I'm still going to send you 2 more where it's, again, the 4 calculator, 4 no calculator, and then the 5th packet, 4 calculator, 4 no calculator. Right? That's a ton of FRQs. Even ones that we've already done, go back and do them again, but do them on your own. Just because you can listen to me do it and say, okay, yeah, that makes sense, but can you replicate it? Right? Go back through and do FRQ questions again, and do them again, and do them again. Right? Until you start to be able to recognize, oh, okay, this is this problem. That means I need to do this type of thing because I need to find this value or this rate or whatever it is. Okay, bury that in your brain. So that's you have so many resources available to you, especially FRQ wise. All right, the 24 I've sent you so far here, the 24 that's on Summit, and then the 16 more that you're going to get in the next 2 packets. Practice them over and over again. Right? Practice. Go through the practice tests on Summit. Do them over and over again. Right? It doesn't matter if you've already seen a question before. Okay. Practicing looking at a question and recognizing what you need to do. That's so important. And it's going to be kind of the make or break in terms of the AP test. Not even just the new AP test, but if you were going into the regular one as well. Okay, so I hope you guys are working on that stuff on your own, right? If your plan is to start working on the AP test next week or the week after that, you're screwed. So I hope you've been starting working on things, and I hope you're continuing to do so. I know you have a lot of crap to do. Trust me. I know. I'm not. I'm not delusional about the amount of work that many of you have for many of several AP classes and things like that. But it's just the reality of the situation that we're all in. Okay. But I hope you're taking advantage of those things and practicing on your own, not just watching me do things. Challenge yourself, test yourself. Sit down and make yourself do questions, even if you've already done them before. Do them over again. Do them over again. Right? Set a schedule for yourself. For, all right, tomorrow or today, I'm going to go back and work on those FRQs from the first one that we did together, the first packet, and then the day after I'll go through and redo the second packet or whatever. But practice these. Keep taking PFAs if you have ones that you need to do. Obviously, AP test is more immediate than PFAs are. After the AP test, you'll still have time to do PFAs, but I don't know. I don't know what the best strategy is for that in terms of timing. When are you going to work on what? But let me know if you need help with anything. Email me with questions or whatever, and I'll do my best to get back to you or help you out or answer whatever it is. And yeah, so we'll start a new packet tomorrow. I'll send you some more stuff. And we will, yeah, I'll see you then. All right, see you guys.